Hello, my name is David Stanleyford and welcome to the CFMS High Order CFD Technologies webinar. It's great to see so many people have joined us today from all over the world. This one-hour webinar is based mainly on work done in the Hyperflux project supported by Innovate UK to develop new high-order methods. We've also included presentations from our technology partners at Pointwise and Hopper. Now there will be a Q&A session at the end of the webinar, so please do submit questions via the web interface. Our first speaker from Imperial College is Dr. Peter Vincent.
So my name is Peter Vincent from the Department of Aeronautics at Imperial College, and I'm going to give a very brief overview of the high-order flux reconstruction schemes that we use for CFD and our open source implementation of these schemes called PyFR. So I'll just start with our motivation for looking at these methods. And it's our contention that the majority of current industry standard CFD tools are designed really for solving steady flow problems using a Reynolds average Navier-Stokes approach. However, there's a whole bunch of problems that are associated with fundamentally unsteady flow phenomena. So for example, vortex-dominated flows, flows at high angles of attack, acoustics problems. And to solve these problems, the current tools are not really fit for purpose. Also, these problems are often want to be solved in the vicinity of complicated engineering geometries. And this is, on the next slide, a quote from the NASA Vision 2030 study, which essentially says the same thing, indicating how current CFD tools are really limited to a nonetheless important but limited region of the operating design space where the flow is really steady because of the inability of current methods to reliably predict turbulent, unsteady, separated flow phenomenon. What we're looking to do is advance industrial CFD from this, what's often called RANS plateau, that we believe it is on, by developing a range of tools for performing scale-resolving simulations of unsteady flows. And we're using high-order flux reconstruction methods to underpin these tools. And we're also interested in using next-generation hardware platforms such as NVIDIA and AMD accelerators. And what I'll focus on in this talk is the flux reconstruction numerical methods. So flux reconstruction schemes were first described by H.T. Wynne in an AIAA conference paper from 2007. The two most salient aspects of the schemes are that they offer arbitrary order accuracy in space, which means they offer, in theory, an efficient route to high levels of accuracy, which you might need for solving these unsteady flow problems we're interested in. And also they can work on unstructured grids, which means that they're very well suited to solving problems in the vicinity of complicated geometries. What I want to do now is describe in the context of a simple 1D scalar conservation law how these schemes work. So we've got a conservation law here, U is our solution, F is our flux of the solution. If we want to solve this in some domain in the X coordinate, the first thing we would do is split this domain up into separate elements, much like in a finite volume scheme. We can map each element, each physical element, we can map onto a standard element between -1 and 1. Inside each of these standard elements, we can define a set of so-called solution points at which we have values of the solution. And we use these solution points to define a nodal Lagrange basis, that's small li in the top right-hand corner of the screen here, that we can use to construct a polynomial representation of the solution inside each element. In this case, this is a second-order polynomial representation, but it can be for arbitrary degree k. Once we have this representation of the solution, the next stage in flux reconstruction is to construct a representation of the flux that we're going to use to update this solution in time. There's various steps to this. The first one is to build what we call a discontinuous flux inside each element, also of degree k, based on values of the flux at each solution point and using the same nodal basis we use to construct the solution. Once we have this discontinuous flux, that's in general discontinuous between elements, we go back to the solution. We take its multiple values at each interface, so a left and a right state at each interface, plug these into some kind of interface flux formula, such as an upwind flux maybe for a linear advection problem, to obtain common interface flux values. So we now have discontinuous fluxes within each element, common interface flux values at the element boundaries. The final step is to propagate information about these common interface fluxes into each element. And to do this, we introduce the concept of a flux correction function. First of all, a left correction function I've called GL here, that's of degree k plus 1, so 1 degree higher than the solution, has a value of 1 at the left of the element, 0 at the right of the element, and oscillates inside the element. The specific form of the correction function inside the element determines various properties of the scheme. We're going to scale this correction function by the jump between the discontinuous flux and the common interface flux at the left-hand side of the element, like so. and now add this scale correction function onto the discontinuous flux such that it now attains the value of the common interface flux at the left-hand side of the element. And we can repeat this procedure from the right. So we take a mirror image of the left correction function, we'll call it GR, the right correction function here, scale it by the flux jump on the right, add this to the semi-corrected flux inside the element, and we now have a degree k+1 representation of the flux inside the element. And if we perform this procedure in all elements, we now have a C0 continuous degree k+1 representation of the flux in the whole domain. We can take the gradient, or in multi-D, the divergence of this flux at each solution point, and we now have the semi-discrete form shown in the top right-hand corner of the screen. So we have the divergence at each solution point, and by suitable temporal integrator, we can update the solution at each solution point to the next time level. That was a very brief overview of how flux reconstruction works for a simple 1D scalar system. We can extend this to multiple dimensions and to more complicated systems. Indeed, we have an implementation called PyFR. Pi stands for Python because it's implemented in Python. FR stands for flux reconstruction, that can solve the Navier-Stokes and Euler equations in multi-D using the flux reconstruction approach. It can run arbitrary order of accuracy on mixed element unstructured grids. It's explicit in time with a range of Runge-Kutta schemes. And one of the most interesting features of the code base is not only can it run on multi-core CPUs, but it can also run on NVIDIA and AMD accelerators using this back-end infrastructure that we have in the code, and also heterogeneous mixtures of all of these platforms. And we've just got a nice paper in Computers and Fluids out that describes in detail its ability to perform compute on heterogeneous hardware platforms. So it's all open source under a BSD license. And I'll point you to the website www.pyfr.org to download it, and also our journal paper in Computer Physics Communications for more details. And then finally, in the last couple of minutes, just to show one of the test cases we've been applying PyFR to. It's flow over a NACA 0021 aerofoil at high angle of attack in deep stall, so 60-degree angle of attack, Reynolds number just over 250,000. There's various computational, so detached eddy simulation data, as well as experimental data to compare with. We've got experimental data to compare with, which is CP time averaged on the pressure and suction side of the aerofoil. The pressure side data is the top dots, the suction side data are the bottom dots. Suction side data is where the flow is fundamentally unsteady. And we can see with a converged PyFR result, we get extremely good agreement for this unsteady test case, at least for CP. So the blue line is the PyFR data. And then also we can look at the spectra of the lift coefficient for this test case. So this is the experimental spectra for lift. And this blue line we superimpose is the result from PyFR, and we capture, it seems, both of these peaks very well. So I'd just like to conclude by thanking my team of PhD students and postdoctoral researchers who do all of the hard work on this project. Our funders, so the EPSRC and Innovate UK, the European Commission, as well as Airbus and BAE Systems, who also support this work via PhD studentships. PRISM, which is a platform for research and simulation methods funded by the EPSRC at Imperial College, and NVIDIA, AMD, and Intel, who generously donated the hardware to support this work. And finally, I'd like to thank the clusters Emerald, Wilkes, and PISDaint, the GPU clusters who've kindly given us access to their systems. So if you have any questions, you can type them in the web interface box. And now I'll hand over to Mark Allen from Xenotech.
Good afternoon. I'm Mark Allen from Xenotech, and I'd just like to give a brief presentation on work that we've been doing under the Hyperflux program with regard to industrializing high-order CFD. So just a brief introduction to who we are. We're based in Bristol in the UK, and we develop computational engineering software primarily for use on the cloud. We have two software packages that we're developing at the moment. So the first being Epic, which is essentially a web interface to high-performance computing around the world, and ZCFD, which is our CFD solver, and that will be the main focus of my talk. So Peter's given us an introduction to flux reconstruction, and so I'd like to just give an indication of the current capabilities we have within the ZCFD solver with regard to our implementation of these high-order schemes. So to begin with, we can take known shape meshes from a variety of sources, and we can see the list of the sources in the flow diagram to the right. And the particular flavour of flux reconstruction we've implemented is the strong form DG method. It's a fully parallel solver, runs on CPUs, and we're able to use GPU accelerators as well. It solves the full viscous Navier-Stokes equations, and those who are interested in doing LES, we have implemented the Whale subgrid scale model. In order to simplify the implementation to allow us to run on various types of hardware, we've implemented the solver using the C++11 standard. The main benefit of this has been that it has allowed us to write common kernels which will execute on either the CPU or a GPU accelerator, and therefore this reduces the development time associated with this. The high order, in order to visualize high order solutions, we write out the solutions in a format that's which is able to be used by a high order plugin from Sebastian Blaze, and we're therefore able to visualize the high order solutions. So with regard to industrializing these high order methods, there are a few issues that we wish to overcome. The first being that high order methods generally rely on explicit time stepping schemes, which result in small time steps due to stability limits. As you increase the polynomial order of the solution, your time step also reduces. Therefore, if we wish to run a time accurate simulation, then typically we would run with a constant time step across the mesh. And for a given simulation period to be simulated, this can result in millions of time steps being required. There are additional issues with high order methods associated with robustness, and this is an area that Imperial College have got a huge amount of expertise in, and therefore we wish to be able to implement their anti-aliasing techniques and so on. And high order methods will primarily benefit those who are at the computationally intense high-end CFD market, so those who are interested in LES, acoustics, and so on. A major focus of our work has been to try and leverage existing mesh generation processes, mainly to allow greater resolution of features which would typically be under-resolved without having to go to incredibly fine meshes. So the convergence acceleration techniques which we have implemented, well, first of all, we've mainly been focusing on convergence to steady state problems. Therefore, the main idea being that if we have an efficient steady state solver, we will be able to wrap it with something like dual time stepping in order to allow time accurate simulations to be done. So first of all, we're trying to make use of GPU accelerators, so therefore it's a bit of a brute force approach. For low Mach number cases, we also have implemented local time stepping and low Mach number time derivative preconditioning, which both of those help us to converge to a steady state. In terms of a usability point of view, we are able to restart lower order simulation, or be able to restart higher order simulation from results from a lower order simulation, and this essentially allows us to minimize the wall clock time required to wash out transients. And then more recently, we've implemented a polynomial multigrid approach, which is similar in concept to geometry multigrid, in that we are trying to remove low wave number errors much more efficiently. And then finally, with an efficient steady state solver, we aim to run something like dual time stepping, which is popular within the finite volume community. So to give an example of the benefits of these convergence acceleration techniques, I have a short video showing the initial propagation of transients out of the domain for oil flow over a cylinder. So on the left will be no acceleration techniques, and on the right we have polynomial multigrid. So as you can see, with the polynomial multigrid solution, we're propagating the initial transients out of the domain much quicker than without any convergence acceleration. And within the 2,000 cycles that have been simulated here, we're already interacting with the far field boundaries. And finally, just to show the benefits with some viscous flow, we have the results here for a Mach number 0.01 laminar flow over a flat plate. So on the left we have convergence histories. So the The purple curve is the case where we have absolutely no convergence acceleration techniques. If we apply polynomial multigrid, we get the green curve, so we can see an improvement in convergence. And then if we apply polynomial multigrid and low Mach number preconditioning, we get the blue convergence curves, so we can see a drastic improvement in the convergence. What this actually results in, looking at the boundary layer profiles on the right-hand side, the purple curve where we don't have any convergence acceleration, we can see that there's very little development of the flow. And then if we start to apply the convergence acceleration techniques, we can see that with polynomial multigrid and low Mach number preconditioning, within these 10,000 time steps, we've almost converged the solution. So thank you very much, and I'll hand over to Andre Sampero from CFMS.
Hello everyone, my name is Andre Sampero. I'm a CFD engineer at CFMS, and today I'm going to talk about some of the industrial challenges and benchmarking as part of the HyperFast project. I'm going to start by introducing CFMS, which is an independent not-for-profit specialist in modeling and simulation, and we mainly support the development of new methods and processes. CFMS was born out as a collaboration between the major UK industrial players, and since 2007 we've been working with aerospace, automotive, civil and renewable companies. On this slide you can see that some of the services that we provide, and we mainly provide a range of services to help organizations to enhance engineering design capabilities. These include benchmark and testing, HPC access, as well as support for projects. Today we are still involved with some of the companies that took part in the core program, and CFMS comes to bridge the gap between the industry and academia by identifying the key technologies and bring them into the industry. One of these technologies is the HyperFlux project. And the main purpose is to, during the HyperFast project, the main purpose is to industrialize the high order methods already available at the Imperial College. During this project, the HyperFast project will make use of the CPU, GPU, and 5 platforms. In this project, 3 partners are involved, but 10 additional partners provided test cases for benchmarking. And the HyperFast project comes to address some of the issues related to most of the engineering applications, such as unsteady vertical flows, highly separated and transitional flows, AD transmissive across siding interfaces, and highly resolved turbulence for acoustic applications. One of the test cases that we looked at is the laminar flow over a delta wing at a Reynolds number 4000. It's a quite high angle of attack, 12.5, and we'll be running this using a steady state approach. This test case exhibits really strong flow features, and since the geometry of the delta wing consists of a sharp leading edge and a blunt trailing edge, as the flow passes the leading edge, it rolls up and it generates a vortex together with a secondary one. In order to visualize the high order data, we've made use of the high order visualization ParaView plugin, which was mainly developed by Sebastian Blaise. And the main idea behind the plugin was inspired from Gmesh, and a polynomial is querying the solution points, and the mesh gets subdivided based on the relative error between the neighboring cells. You can see here the same solution visualized using the ParaView cell data to point data interface, and the high order data visualized using the plugin. You can see a really big difference between the two. On this slide, you can see a difference between the polynomial, the P2 polynomial, and the second order finite volume. You can see that we have quite a high number of degrees of freedom compared with the second order finite volume, but the main purpose of this was to look at the benefit of using high order methods. So we can take the existing mesh, you can take the existing mesh and run the flux reconstruction technique on the existing mesh without actually refining the mesh. A much better comparison, I have it here on this slide, where we compared the second order finite volume, the existing mesh, and against the different order of the polynomials. And you can see that the a lot more physics is captured as the polynomial order is increased, but the computational time increases quite dramatically. But by comparing just the P1 polynomial with the second order finite volume solution, you can see that these methods really capture the pairs of vertices very well. The next step was to look at how well these vortices are preserved in the free stream. So what you see here is an isosurface of the density level of 1.2, and the isosurfaces are colored by the velocity. You can see here that the finite volume solutions does not capture the pairs of the vortices very well, as you can see here, and whereas the P3 approach really captures and also really propagates and preserves very well the vortices in the wake. Having said this, we identified some industrial challenges related to engineering applications, such as the high Reynolds number flows. As my colleague Mark Allen mentioned, these higher order methods will benefit only for using advanced turbulence modeling, such as LES and ILES. And for high Reynolds number flows, the main issue will be related to the near wall, since in that region we have very small grid, very small cells, and hence the time step associated with these cells gets very small, and therefore the CFL, which will drive the convergence. So for these kind of flows, we will tend to obtain a very long time in the simulation. The other issue is to scale to resolve as much as we can for acoustic applications. The other thing is to mention that the post-processing role is already a challenge, since most of the post-processors available in the industry, they analyze finite volume solution, and for solution polynomials there are not that many. So we used this plugin in order to visualize the data, but work is being done, so it can be used using the Catalyst utility available in ParaView. The other issue is that we can reduce the convergence by using less elements, and by using less elements we can actually generate very coarse meshes, but also the main point is to generate curved elements near the wall, and this will lead us to less elements per overlap, and hence a faster convergence. If you have any questions, I'll be happy to answer at the end. Thank you very much, and I will introduce you to the next speaker, Steve Carman from Pointwise. Thank you very much.
Thank you. My name is Steve Carman. I'm at Pointwise. I've been at Pointwise since December of last year. Previous to that, I was at University of Tennessee. Here at Pointwise, we've been working in higher order mesh generation concepts for a few years now, and I'm going to show you some of the research that we've been doing. I will cover 4 or 5 different methods that we've been looking at for doing higher order mesh elevation. Pointwise generates structured and unstructured linear element meshes, and the first method is going to talk about elevating those using a script on export, and then I'll follow that with 3 methods of doing different types of smoothing and interpolating, and then finally talk about an optimization-based method, and then leave the final results with future developments. Travis Harrigan started working on this concept 3 or 4 years ago, and basically he's going to use Pointwise for the linear mesh generation, and it's going to be constrained to CAD, and then he'll elevate those elements to higher order, and through scripting, place the points on the surface and export the higher order mesh. So these are the steps that would be involved in that process. You generate a linear mesh. You build the higher order faces and edges and cell data. You compute the internal node locations and then project those surface nodes onto the CAD. In this step, there is some interpolation going on, but it's only near the actual surface. So then you construct the higher order elements and export the element connectivity and the boundary conditions. So this was work that he did with Cameron compression systems and was demonstrated in ASME Turbo Expo paper. It's specialized for the specific application. It's not quite generalized yet. The next few methods were performed by summer interns here at Pointwise, students that were my students at University of Tennessee. The first one is going to use linear elastic smoothing. This is a common method used in moving meshes. You borrow the equations from structural mechanics and that describe the deformation of interiors of solids based on forces applied to the surface. So in the mesh generation realm, you treat the mesh as a collection of deformable elements, and the stiffness is defined by some shape information. Usually higher aspect ratio elements are more stiff. You could also use the inverse distance to the wall as a method for defining Young's modulus. So then you compute the interior node perturbations based on the prescribed boundary perturbation values. This slide shows the result of elevating two different meshes to the surface of an airfoil. The top one is an inviscid type spacing, so larger elements, but it's a fourth order polynomial that's being used. So you can see near the leading edge there are quite a large display of the surface, and the curvature of the mesh is evident in the interior. And then the bottom image is a highly packed mesh, and you can see that it's still successful at deforming the mesh and generating valid elements in this case. The next two methods are going to be interpolation methods. The first one is radial basis function interpolation, and this follows some of the work by Rendell, Allen, and Chen. You basically define a function that's a linear combination of basis functions, phi, and source points, s. So you generate this equation set, you have unknowns, alpha. So what are the possibilities for phi? Well, here are some of the more common ones. These provide global support, meaning they provide support over the entire domain. R is going to be a distance from a source point to the actual interior point. And the more commonly used ones on this slide are going to be the multi-quadric, the inverse multi-quadric, and the thin plate spline. Here are some basis functions that provide compact support, meaning they don't require the knowledge of the entire domain. It's just a localized influence. And there are different levels of complexity here. The next method is mean value coordinates, and this follows some work from Horman and Floater. And they're using basically area coordinates. So triangles have a property that you can describe, generate some area coordinates, A1, A2, and A3, that are barycentric coordinates of the node B. So based on this triangle, V1, V2, V3, you can actually use this geometry to do interpolation. So if you subtract V from all of those different locations in the triangle, and then you can assume the denominator is positive, you can take that out of the equation, and then you can generalize this further to a n-sided polygon here. So you got V is your point of interest, VI are your boundary points, and W's are weights. And you can normalize these, and you can end up with generating a interpolation scheme for interior value based on the boundary values here. So this is for the coordinates. You can then expand that, interpolate a function instead of just coordinates. And for the current applications, we're going to interpolate the displacements, U and V, or delta x of I. On this slide is the results from the linear elastic radial basis and mean value coordinates. The geometry is a simple geometry, but it's very highly nonlinear and curved on the top side. You can see the shape on the upper surface. The green lines are the linear triangles. So you can see there's a triangle that spans this incredibly deep divot, and then another triangle over here where there's high curvature. The bottom is relatively flat, but there's a sharp point on the lower left corner. The top left image is the linear elastic result. You can see that it did not properly elevate the mesh at this upper side. The top right is the mean value coordinate results. It does a little bit better, but it's still an invalid mesh. And then the radial basis is on the lower left. Again, it's better than the other two, but it still is not quite a valid mesh. So there's some issues with these methods for these highly curved boundaries. The final method is something I've been working on for quite a number of years. It's optimization-based smoothing of linear meshes. And you devise a cost function. You try to move the nodes around to maximize the element quality. In this scenario, I'm going to subdivide the higher order elements into a collection of linear sub-elements, and I'm going to prescribe their shape. Then I'm going to prescribe the perturbation of the higher order surface nodes, and then smooth the collection of linear elements to optimize the sub-element shapes. And then once that's done, we will delete the sub-elements and recover the higher order mesh. And all this is based on some smoothing methods that was presented last January at the AIAA SciTech conference. The cost function in this case is 1 over condition number. Condition number is a mathematical term, but it's used here to express the conformance of an element to its prescribed shape. So A here, the A matrix is the Jacobian matrix of the actual element. So the columns are actually edges coming from a corner. The W matrix is the prescribed shape that I'm trying to impose on this element, and you can see in the diagram below the element shape is rather arbitrary. If I was doing regular smoothing, I would make this an equilateral triangle. So what's going to happen with the higher order elevation is I'm going to take a linear element and subdivide it into sub-elements that have the prescribed locations of these higher order nodes. So I show a triangle on the upper right and a quad on the lower right. Then I'm going to use sensitivities of this cost function to decide how to move these nodes around, and I'm going to perturb them in an iterative fashion, trying to drive the element costs to the perfect cost value of 1. This shows how this method would work. If you look at the lower left, there's a second order triangle that has been placed on a boundary. Green is the boundary, and you project the surface node, in this case a lower mid node, up to the surface shown in the upper left, and you would see you get an element inversion here, an invalid element. But in the method that I'm using, I'm going to subdivide this triangle into 4 subtriangles. I'm going to impose that shape, the shape of the parent element, as the desired shape. And then when I project that surface node up to the green surface, the linear sub-elements end up conforming and moving in the proper manner. Same can be said for a quadrilateral element. Again, I have the green as the geometry. I'm going to project the mid node on the bottom. And if you do this without any smoothing, you're going to get a crossed element. Whereas if you generate sub-elements and then move that bottom mid node, the interior nodes will then naturally move in a nice orderly fashion and give you valid meshes. So here's an example of this being applied to a triangular mesh for 4th order elements. It's a circle within a circle, and then there's a highly refined region near the inner circle with large, long triangles, and the figure on the left shows the elevated mesh. As you can see, there's dots that are the locations of the interior nodes of the higher order element, and the mesh is conforming to the boundary and then naturally gradates away from the surface in a nice fashion. The same case was run with quadrilateral elements, and you can see a similar result. It looks like these are actually grid lines, but they're actually collections of dots of the higher order element. So this is a highly packed mesh, and it's very successful. So then applying that method to the wavy case that was unsuccessful at the other three methods, the figure on the left is an all triangular mesh, fourth order elements. You can see that it's getting valid elements at this on the upper side. There's no crossing that's taking place. The figure on the right is a quad dominant mesh. So most of the elements are quads, but there are some triangles. This is actually a triangle here, and there are triangles there. So it's very successful. Again, it's generating valid higher order elements. So our intent is to implement the 3D mean value coordinate system interpolation. Right now it's only been demonstrated in 2D. We want to develop the higher order optimization smoothing, and that's underway as we speak. And I think the strategy that we're taking is that we want to use the mean value coordinate as an interpolation scheme to initialize interior node locations, and then the optimization smoothing will take over and improve the mesh quality. And we're having discussions right now as to whether this should be a post-processing step like the scripting that was done previously, or included in the internal data structures within pointwise. I suspect that we'll probably do both, the glyph scripting first, and then internal at some future date. If you have any questions, you can send them through the webinar, or you can email me at my address there. Thank you.
Yes, hello. So my name is Florian Hintenlang. Hope you can all hear me. I first want to thank the organizers for inviting me, and I will give you an overview on the high-order preprocessor called Hopper. So we are doing discontinuous Galerkin methods, and we know that they are high-order accurate on unstructured grids. But once you have a curved wall boundary, you need to maintain this accuracy using curved elements. And we're interested in discontinuous Galerkin for industrial applications, so wall-bounded flows, 3D geometries, and unstructured and coarse grids. And that's why we developed the Hopper, and it's already released open source. You can check it out under hopper-project.org. It's a mesh preprocessor for parallel high-order simulations, so I think you can use it for DG, Flux reconstruction, spectral elements, high-order finite elements, and so on. It's written in Fortran. You can generate simple meshes for testing directly in Hopper, and more important is the Hopper input now. So you can use unstructured hybrid meshes from any grid generator. We have several formats supported for reading, mostly used as CGNS, and I will show you here in this short talk some strategies we are applying to the initial linear mesh to produce high-order meshes. Just first thing, we do have an output of a HDF5 mesh file. I want to show you here because our idea was to generate a mesh file which can be directly read in parallel. And so first of all, Hopper does a sorting on the elements along a space-filling curve. This generates a 1D element list, and then it's easy to split this into an arbitrary number of domains. And in addition, now we have an element per element data blocks where you have the high-order node coordinates, all of them, the site informations for boundaries and connectivity. And now when you do the read-in, you can directly split up the global arrays into non-overlapping blocks during the parallel read-in. So for example, the node coordinates here, you have different blocks for 3 processors in this example, and each block is a continuous one and it's not non-overlapping. So this is really smooth. And these are the different strategies we are doing for mesh curving. And I want to start with the first one, the point normal approach, where we start with a linear unstructured hybrid mesh and we use normal vectors at the surface nodes. And we get these normal vectors either without any additional data, so we reconstruct from the linear surface, or we have an analytic function, so for spheres and cylinders you can write this down, or you can also input an additional point normal file so that every point gets associated normal. Once you have the normal at the edges, you can generate curved edges, so here shown with Bézier control points. And having multiple normal vectors is also supported because you want to recover also sharp edges and corners as shown in the plot below. And once you have the curved edges, you will generate the curved face by superposition of blended pairs of curved edges, called so-called Kuhn's patches. A second strategy to get the curved boundary faces is surface subdivision. There you need the unstructured hybrid mesh again and a subdivided surface mesh. And this is how it looks like. So you have a initial linear coarse mesh, and your mesh generator basically allows for subdivision of this mesh and keeps the new points on the CAD surface. So these are two steps of subdivision, and now you can read in this surface mesh in addition to the linear volume mesh, and we generate by interpolation polynomial surface patches. And from these polynomial surface patches, we get the element mapping by simply blending first the adjacent faces, and then we have a blending for the volume mapping, and this can be generalized for all element types. And here just a quick example of a very coarse mesh. It's a wing body nacelle configuration. We have hexahedrous prisms and tetrahedrous, and here you can see the curved elements of the first element layer. The green sides are the curved sides, and we visualized also the surface mesh. So this is really the polynomial patches visualized, and you see that it's basically looks like the CAD surface, but it's really the polynomial patches, I guarantee you. And you can see sharp edges still in the mesh. The third approach I want to show you is when you start with a block structured mesh and you agglomerate the sub-blocks. So this might be something that was also done by Pointwise with this post-processing script. The idea is to start from a fine block structured mesh, which you can see and hopefully see in the gray lines, and you coarsen this mesh by a fixed factor and use the inner points to generate a high order element mapping. And Andrei Chupero, sorry, I did it wrong. You're not from Imperial College. He provided me a test case of this serrated nozzle, and it's 85 blocks, 20 million linear elements, and half a gigabyte of CGNS file. And we managed to agglomerate this, so we used 4x4x4 elements to agglomerate to one high-order element. So this gives around 300,000 P4 elements. And Hopper used about 6 gigabytes of RAM and was running for 2 minutes, where 1 minute was spent to eliminate multiple duplicate nodes, which is quite important, and 40 seconds were spent in the Jacobian checker, which is also important. And when we did this, first of all, we checked that the linear mesh was valid. So here we have all elements are linear, and we look at the scale Jacobian, and it's valid for this mesh. And once we curved all elements with this agglomeration approach, we saw that inside the volume we had some negative Jacobians, so invalid elements. And clearly, if we only curved at the boundary, the wall boundary condition, we also got invalid elements at the boundary. And now we implemented a function where we could choose a number of layers around the curved geometry to remain curved in the volume, and the rest of the mesh would then be linear. And as you can see, if we only use one layer, we still have some invalid elements. With 2 layers, we have a valid mesh, and we can also extend this to 3 and 4 layers, and the mesh is valid and the quality increases. And now I want to just mention some ongoing work with boundary layer meshes. As you have seen, that the agglomeration approach already works fine, and you can have boundary layer meshes already curved. For unstructured grids, we do only the curving of the first element because we only have the surface curving up to now, and our ideas are twofold. The first idea would be if we have a prismatic layer of linear elements like shown in this sketch, we could do the blending instead of only for the first element, we could do it for the whole stack of elements, and then this would result in a valid mesh. And the second strategy would be to insert boundary layers afterwards. Both of these features are still not released, but we are planning to do this. This is an example of this splitting of introducing the boundary layer afterwards. So we have a valid curved mesh, and we have hexahedrons or prisms at the boundary. Now we can split the first layer into a given number of boundary layer elements, and also with a given stretching. These are input parameters, and then we would have a valid mesh with a boundary layer. So this would be my talk. I showed you that we can provide unstructured high-order meshes. We have different curving strategies depending on the provided data, and you can have a HO mesh file which is directly designed for parallel I/O. The software is open source, and an announcement for the next ICOSA home. David Kopriva asked me to do this. He wants to organize a mini symposium to discuss a standard for high-order mesh format, because this is still an open issue, I guess, up to my knowledge. Okay, thank you very much for your attention. You can check out the homepage. We have a mailing list, tutorials, documentation. You can also contact me via email or Thomas Bohlemann too. So thank you very much.
Great, and thank you very much to all of our speakers. We do have some time now to answer some questions. Perhaps we'll start with an easy one. The question is, are the tools available for use now? And the answer is yes. You've already heard from the presentations on the mesh generation side that those tools are available, or what their availability will be. On the solver side, of course, PyFR is available for download in the website that Peter showed you. By the way, there'll also be a summary of those links at the end of this webinar. ZCFD is available for use, of course. This is an open innovation project, so that the tool is available at CFMS now, and that Flux reconstruction technology will be included as part of a major code release next year. Great. Okay, slightly more complicated question now. It's how do the performances of the finite volume and Flux reconstruction code compare with the same number of degrees of freedom, i.e. the same computational effort? Okay, now that, of course, there are numerous aspects in answering that question. It sounds very difficult, so I'm going to refer to Peter Vincent now to deftly handle an answer to that question.
Okay, thanks, David. Yeah, it's a good question. I think it's still an open question to some extent. All I can say is that in the studies we've done at Imperial College comparing PyFR with industry standard finite volume solvers, we get order of magnitude performance increases in terms of accuracy and runtime, at least for the test cases that we've been running on. But obviously, there's work to be done at the sort of industrial level, I think, to ascertain exactly quantitatively what the benefits are.
That's fair enough. Yeah, I think there's been some publications recently where some benchmarking was done with some commercial code.
Yeah, there was an AIAA paper on this.
Yeah, okay. Also, just a clarification there, can we use a standard finite volume mesh and then generate a Flux reconstruction or DG solution? To pick that one up, I'll maybe answer that one. Yes, you can. In fact, one of the principal objectives of this project was to ensure that the end-to-end CFD workflow for end users would be sort of minimally disrupted by the option to use Flux reconstruction, effectively so that you can dial up the order of accuracy in the solution without needing necessarily to regenerate the whole of the mesh. So yes, I think Mark Allen in his presentation included a description of the kind of mesh formats that were currently supported by ZCFD, and obviously we've now had, I think, a very stimulating proposal about the common high-order mesh format for the high-order schemes. So, so yes, the intention is that there will be minimal additional requirement to be able to run those high-order schemes. Okay, I'm not seeing any more questions at this stage, so I think we're pointing you now to some links, some resources online. Some of them are the codes, we have some partners, and of course we're ever grateful to our funding agencies. Thank you all very much for joining this webinar.